There are other needs of man that can be measured in miles and acres. Miles of grueling travel over land and sea, imposed by unfriendly terrain. Miles of hauling goods to distant ports. Acres of potentially rich, inhabitable land laid waste because it is cut off from civilization. Or hungry, thirsty villages cut off from water that may be but a few short miles away beyond a natural barrier. Needs like these, expanding economic and social needs of an ever-expanding population, can be met only by moving huge quantities of earth efficiently and economically. For these immense projects, in air relatively isolated and underdeveloped, nuclear excavation offers the potential for providing the practical economical means. Where present land travel is awkward, costly, time-consuming, and dangerous, excavating mountain passes for highways and railroads. Where water navigation is thwarted by imposing barriers of earth, excavating canals. Where commerce is stifled by forbidding shorelines, excavating harbors. For the diversion of water, cutting channels of great width and depth to carry water to areas of need. Nuclear excavation also presents great potential for industry. For example, in the quick and economic removal of earth overlying deeply buried mineral deposits. The basic task in developing plowshare excavation technology is to answer this question. In order to produce a large crater with specific dimensions in a specific earth formation, what size explosive is required and how deeply should it be buried? Conventional explosives are routinely employed for construction and mining operations. They have been used on occasion to remove massive obstructions to commerce. A few years ago, nearly 1,400 tons of chemical explosive decapitated the submerged pinnacles of Ripple Rock that had imperiled ships using the inland passage northwest of Vancouver, British Columbia. But to produce enormous craters with scientific precision, plowshare scientists must start with the blackboard, the slide rule, and the computer. They must develop new scaling laws and mathematical models for relating the results of these smaller explosions with the requirements for larger explosions, nuclear explosions in the hundreds of kilotons and the megaton ranges, which will be needed for major earth-moving projects. Computers take these mathematical models and theoretically fire nuclear explosives, giving a picture of the effects and end results expected in a particular earth formation. A major step was taken in July 1962 to develop the technology and safety requirements for the immense excavation projects toward which Plowshare is building. This was Project Sedan. The 100-kiloton nuclear explosion excavated more than 6 million cubic yards of earth in a matter of seconds. The result was a crater more than 1,200 feet in diameter, the length of 4 football fields, and 325 feet deep, the height of a 32-story building, created in less time than it takes to describe it. To clear a volume of rock the size of the Sedan crater with conventional methods would require more than 2,000 tons of chemical explosives and 25 pieces of heavy earth-moving machinery over a period of at least 6 months. Estimates like this have prompted experts to consider using nuclear explosives to do these immense tasks never before economically feasible. But as man looks to the potentials, he is not overlooking the problems. Obviously, the same characteristics that enable nuclear explosions to perform enormous useful tasks can also present hazards if they are not properly controlled, particularly in excavation projects. These potential hazards, except radioactivity, are encountered to some degree even in large chemical explosions. The results of plowshare work in controlling and limiting the radioactivity released by a nuclear explosion have been and continue to be highly encouraging. scientists have already determined that when nuclear explosives are buried at the depth that will produce the biggest crater, a major part of the radioactivity is swallowed up in the rubble of the crater. But the most promising results have been gained by improving the design of the explosive itself and by improving emplacement techniques. Both of these specifically calculated to reduce the release of radioactivity. In the 1962 Sedan event, for example, only a small fraction of the radioactivity produced by the explosion was released to the atmosphere. If Sedan were conducted with the improved design and techniques available today, there would be even less radioactivity, and more reduction is still expected. 100-fold reduction from the radioactivity levels of 1962 through more improvement in explosive design and emplacement techniques. When this prediction is realized, it will mean that the main limitation on nuclear excavation projects will not be radiation. It will be the other potential hazards of explosions, nuclear or conventional. The ground shock, the air blast, and the dust cloud. Just as with radiation, these other safety problems are subject to control by selecting the minimum yield necessary to do the job, by thoroughly examining the local earth structure and local buildings, by timing the event for the right weather conditions, and by temporarily relocating people and livestock. Each of these potential hazards is being carefully studied to determine the exact controls that will be needed in future large-scale projects. Although single nuclear explosions to form circular craters like Sedan have been used to develop basic technology and safety requirements, far more practical value is expected from detonating nuclear explosives in rows to form long ditches. Men have visualized the uses for this type of explosion in digging enormous mountain passes and huge canals. Several projects have already been suggested to PLOWSHARE. A typical mountain cut would be like the one suggested in California's Mojave Desert. Demands placed on railroads and trucking for faster schedules, and the motoring public's demand for greater efficiency have led to a closer examination of one of the West's major transportation arteries. Rerouting railroad and highway traffic over the most direct path through the Mojave Desert, saving countless dollars and man-hours, would mean cutting through an imposing barrier, the Bristol Mountains. It would mean excavating a mountain pass 2 miles long, moving 68 million cubic yards of earth. This project, or a similar mountain cut, would be an effective demonstration of PLOWSHARE's potential with rows of nuclear explosives, if all of the safety requirements can be met. But there is no doubt that most applications for nuclear excavation would be not in the United States, but in other countries. The most dramatic example so far is in Central America, the blasting of a sea-level Atlantic-Pacific interoceanic canal. Studies are being planned for both conventional and nuclear excavation on 4 possible routes for such a cut across Central America to supplement and eventually replace the Panama Canal, where ships now wait long hours to strain through the narrow, complex lock system, and others can't make it through at all. Before long, it will be inadequate. Even before it was built half a century ago, the complexity and limitations of this lock-type canal were realized. Men dreamed of a sea-level canal, but it remained a dream. PLOWSHARE may be able to make that dream a reality, and it is being considered. It is estimated that for certain routes, nuclear explosives could excavate the sea-level canal at 1/3 the cost of conventional excavation and in considerably less time. And the end result would be a much wider and much deeper channel. A nuclear-blasted route across Central America could provide a navigable channel 1,000 feet wide and up to 200 feet deep in mid-channel, offering a virtually unlimited capacity. No wonder this enormous project has so stimulated the imagination of the world. For a canal of this immensity, representing years of planning and development, complex engineering, and precise execution, would be one of the greatest civil engineering feats of all time. And so the planning and the search for more needed information go on, as PLOWSHARE builds toward the technology needed to accomplish the proposed projects we have seen, or any other projects of equal magnitude. Basic results of peaceful nuclear explosions have been demonstrated in moving huge quantities of earth, in breaking and fracturing masses of rock deep underground, and in providing man with new scientific knowledge. But these results are still potentials, and much work remains to be done before these potentials can be turned into the realities that will serve the specific needs of men in various parts of the world. When any one of these specific applications comes to pass, whenever the time and whatever the place, it will mean that in experiments like the one being prepared for here, the technology and safety of peaceful nuclear explosions have been thoroughly developed and demonstrated. Furthermore, when nuclear explosives are chosen to do a job, it will mean they are doing a large job cheaper than could be done with conventional methods. Or, more likely, it will mean they are doing an immense job that would be impractical because of time and costs, or even impossible with conventional methods. This is the peaceful potential of nuclear explosives that the United States is developing for all mankind. In the program it calls PLOWSHARE.